All right, let's get right into it. We are absolutely swimming in data these days, right? But what if I told you that pretty much every number we collect, every single data point, is telling a tiny little lie? Today, we're going to talk about those built-in imperfections in our data, and more importantly, the really powerful tool we can use to see right through them.
It really does. You can think of any data set like an iceberg. The numbers you see on a spreadsheet, that's just the tip, the part that's sticking out of the water. But the real story, the true hidden structure, is all happening underneath the surface. And this is the million-dollar question for anyone who works with data, isn't it? If every single measurement we take is a little bit off, a little bit flawed, how on earth do we ever get to what's actually going on? Well, there is a way, and we're about to break it all down.
So, first things first, before we can find a solution, we have to really understand the problem. Let's get up close and personal with this idea of error that's hiding in all of our data. So, what even is measurement error? It's actually super simple. It's just the gap between what's real and what we manage to write down. You know, like when you step on a bathroom scale. 1 second it says 175 pounds, the next it says 175.4. Neither of those is probably your exact true weight. That tiny little difference, that's measurement error in a nutshell. And this stuff creeps in from all over the place. You send out a survey and someone might just guess an answer because they don't know for sure. Or maybe they totally misunderstand what you're asking. We also see it all the time when people say they'll do one thing, but then their actions tell a completely different story. And a really big one is when we try to measure some huge fuzzy concept like economic health using a simple proxy like GDP, which we all know doesn't capture the whole picture. It's just an unavoidable part of the game.
And look, this isn't just some small academic annoyance we can ignore. This noise, as we call it, can completely change our conclusions. It can point us in the wrong direction and lead us to make some seriously bad decisions if we're not careful.
Okay, this is where the rubber really meets the road. If you have some error in your outcome variable, the thing you're trying to predict, your results get a little less precise, a bit fuzzier, but they're still basically pointing in the right direction. But, and this is a huge but, if the error is in your input variable, the thing you think is causing the change, the whole model gets warped. Your results become biased. That doesn't just mean they're fuzzy, it means they are systematically wrong. It's like trying to navigate with a compass that's permanently stuck pointing 20 degrees off. It will consistently and confidently lead you astray.
So, if our data is inherently noisy and imperfect, what are we supposed to do? Well, it turns out we have a tool designed specifically for this job, a way to peer right through that fog.
Let me introduce you to factor analysis. The best way to think about it is like a bridge. On one side of the bridge, you have all the stuff you can actually measure. Survey answers, economic numbers, you name it. And on the other side, you have these big, important concepts that you can't see, the things that are really driving the whole process. Factor analysis connects the two.
The key idea here is something called a latent variable. Now that sounds technical, but all it means is a hidden cause. We can't measure it directly. For instance, a scientist can't just go back in time and measure the paleo-environmental conditions from 10,000 years ago. But they can infer what those conditions were by looking at things they can measure today, like tree rings or pollen found in lake beds. That hidden concept, the environmental conditions, is our latent variable.
Okay, so how does this machine actually work? Let's pop the hood for a second and look at the basic mechanics. It's actually pretty clever.
So we start with what we call our indicators. These are the concrete, observable data points that are right there in our spreadsheet. If we're looking at the economy, our indicators would be things we can measure, like GDP growth, the employment rate, and the inflation rate. Think of these as the symptoms we can see.
What we're really after is the factor, which is our latent variable. In this case, that would be the big abstract idea of overall economic performance. The whole assumption is that this single underlying force is what's causing our three separate indicators, GDP, jobs, and inflation, to move in related ways.
And here's the real magic. Factor analysis takes each one of our indicators, let's say the employment rate, and it splits all of its movement, all of its variance, into two separate piles.
The first pile is called communality. This is the good stuff. This is the signal. It's the part of the employment rates movement that it shares with GDP and inflation. It's the portion that can be explained by that hidden factor we're calling overall economic performance. Then you have this second pile, and that's called uniqueness.
This, my friends, is the noise. It's the part of the employment rate's behavior that has nothing to do with the other indicators or our hidden factor. This is the measurement error, perfectly isolated and set aside so we can focus on the real signal.
Now, of course, this isn't just some philosophical idea. It's a real statistical method, and it comes with some important rules you have to follow.
Before you even think about running one of these, you have to make sure your data is actually suitable for it. First, you just check to see if your indicators are even related to each other. I mean, if they aren't, there's probably no hidden factor connecting them, right? And then there are formal statistical checks, like Bartlett's test and the KMO test, that give you a green light telling you that, yes, your data has the right kind of structure for this to actually work.
Okay, now, for those of you who've been around the data block a few times, something about this might be sounding familiar. Let's clear up a really common point of confusion.
You might be sitting there thinking, hold on a minute, this sounds an awful lot like principal component analysis, or PCA. And you know what? That is an excellent question, because on the surface, they look very similar, but underneath, they are fundamentally different creatures.
The whole difference comes down to their goal, their philosophy. Factor analysis is like a detective. It assumes there's an underlying cause, our hidden factors, that are making our observed variables move together. It's trying to explain why they're correlated. PCA, on the other hand, is more like a librarian. It's not looking for a hidden cause. It's just trying to take a huge, messy pile of information and neatly summarize it into a few key themes or components to make it easier to handle.
So if you're going to remember one thing, let it be this. Factor analysis is digging for the why. It wants to understand the hidden causal structure. PCA is just summarizing the how. It's creating a simpler, condensed description of the data. One is about explanation, the other is about summarization.
And at the end of the day, that's what this is all about. We know our data is messy. It's full of static and random bumps and all sorts of imperfections. Factor analysis gives us a disciplined way to filter out all that noise so we can finally hear the true signal hidden underneath.
And that really leaves us with one last thought. This idea isn't just for data scientists. Think about your own life, about the world around you. Think about things like consumer trends or political opinions. What are the things you can see and measure, and what are the deep, hidden factors that might actually be driving them? Once you start looking for them, you'll start to see them everywhere.